In the 1800s, the town of Dijon in France struggled with access to clean water. Fortunately, Henry Darcy, an engineer and dedicated public servant, found a solution. He designed one of the first modern public water supply systems, the fountains in Dijon. As part of this work, he studied fluid dynamics and developed an equation that is now known as Darcy's law. This law appears in the appendix for a guide for water engineers to plan and construct domestic public water supply systems. And the law came out of filter studies in which Henry Darcy conducted lots of experiments on the devices just like you see here on the right. And in case you wondered, Dijon is the regional home of Dijon mustard. So the Darcy law relates a flux to a driving gradient. And to complete the equal sign, one needs to have a factor of proportionality, which is what the saturated hydraulic conductivity is. And the saturated hydraulic conductivity incorporates fluid properties, such as viscosity and density, as well as features of the pore system, such as pore structure, connectivity, and tortuosity all in one. So now let's apply the Darcy law to the little setup on the right. Here we have a horizontal soil column which has a length L and a cross-sectional area A. To the left we have an inflow reservoir, and to the right we have an outflow reservoir. If the setup is such as it is drawn here, where the inflow reservoir and outflow reservoir are at the same height, we would have no flow. That is because we would have no driving gradient. The change in height over the length of column, as implied in Darcy's law here, would be zero because both of these are at the same height. So delta H would be zero. Now what happens if we drop the water level in one of the reservoirs? So now we have a driving gradient, delta H, between the inflow and the outflow side, which would create a flow of water in this direction. And remember, the flow always happens from areas of high potential to low potential. So in this example, from the inflow to the outflow side. So now let's do the experiment that Henry Darcy conducted to come up with the law that is named after him. So we're going to make a little graph on which we will plot measurements of flux, volume per area per time, and of the driving gradient. And we're going to do it by switching out the soils that we have in our system. So for a first soil, we collect data such as this. And for a second soil, we create data such as this. Now, if you look at them, you see that it implies a linear trend, and indeed, a linear trend can be established with this data. Which means that the saturated hydraulic conductivity is simply the slope of this line. So now that we have the two soils in here though, which one do you think would be most like a sand and which one would be most like a loam? In order to figure this out, let's use what we already know about flow in porous media and soils. For the red soil, we need a relatively low driving gradient to have a relatively high flux, compared to the green line, which means that for the exact same driving gradient, we would have a lower flux. So the red line would maybe be representative for a sand, whereas the green line would maybe be representative for a loam soil. And if we wanted to add a clay soil to it, it probably would have a behavior such as this, meaning that in order to have the same flux as the sand and the loam, we would need a higher driving gradient to establish that. Now, to put some numerical values on the slope or the saturated hydraulic conductivity of these soils, we might say that sand would have something in the order of 500 centimeters a day. A loam may be in the order of 50 centimeters per day. And a clay soil may be in the order of 5 centimeters per day. So let's do a little example calculation. Let's say we have a soil that has a saturated hydraulic conductivity of 50 millimeters per day, and we have a soil column that is 100 millimeters long. On the left side, on the inflow side, we have a water reservoir height with respect to the soil column that is 70 millimeters. And on the right side, on the outflow side, we have a height of water of 20 millimeters. Now in our Darcy law, we calculate our flux, volume per area per time as minus saturated hydraulic conductivity times the driving gradient, delta H over L. And the delta H we are going to be calculating as out minus in. And that is so that we are consistent with the sign convention that is in this equation as the minus in front of the saturated hydraulic conductivity. So let's plug in our values, and we have minus 50 millimeters per day times 20 minus 70 millimeters divided by 100 millimeters. And that comes out to be 25 millimeters per day. And note here that the units of the flux are the exact same as the units of the saturated hydraulic conductivity. But as you're doing these calculations, always remember that they represent two very different things, even though they have the same units. So now let's do one more example, but on this example we turn our soil column vertical, so we rotate it by 90 degrees and establish flow in the downward direction rather than the sideways direction. In order to do this, we are ponding water on top of the soil column. And let's say we're ponding 20 millimeters of water on top of the soil column. Now we need to talk about our driving gradient, and specifically we need to talk about that change in potential which makes the flow happen. We said previously that that is the potential at the outlet minus the potential at the inlet. And for the horizontal flow condition in the previous example, we only had a pressure potential or pressure potential difference driving the flow of water. But now in our vertical example, we also have gravity acting on the water and contributing to the flow of water. So our delta H here now becomes the sum of the pressure potential plus the gravitational potential acting at the outlet minus the pressure potential plus the gravitational potential acting at the inlet. So what is the pressure potential? At the outlet, the pressure potential is equal to 0. And it is 0 because water is freely dripping out of the soil column. If I were to put my finger there, we would build up a positive pressure there. But because I don't have my finger there, water drips out and we have a 0 pressure potential. At the inlet, we have a pressure potential of 20 millimeters, which corresponds to the height of water standing above that surface. For the gravitational potential, I do have to define a reference elevation within our system. And the choice of this reference elevation is more or less arbitrary, and I may just choose my outlet as my reference. And calling this the reference really just means that I assign the gravitational potential at this location to be equal to 0. And now the gravitational potential at the inlet would simply be the height above the reference, or 100 millimeters, which corresponds to the height of our soil column. So now we're ready to calculate. We have a volume per area per time equal to minus Ks times delta H over L, which is minus 50 millimeters per day times the pressure potential at the outlet as well as the gravitational potential of 0 minus the pressure potential of 20 millimeters plus the gravitational potential of 100 millimeters divided by 100 millimeters equal to minus 50 millimeters per day times 1.2, which equals 60 millimeters per day. So what does the 60 millimeters per day really mean? So we said on the soil column at the bottom, we are collecting a volume per time that goes through the soil column and goes to a cross-sectional area corresponding to the size of the soil column. If I divide the volume per time collected at the bottom of the outlet by that cross-sectional area, I would derive at a flux equal to 60 millimeters per day. But 60 millimeters per day also means that if I had a waterfront that I observed, let's say at this height, and I wait exactly 1 day, I would find that this waterfront would have advanced 60 millimeters in 1 day.